Hello students, this is Mr. Bornheimer, and today this is for a chemistry video, and today I'm just going to briefly go through kind of what we went through in class concerning phase changes. If you were confused about the idea of phase changes, this might be a good video for you to watch just because it does clarify some of the terminology, and when it comes to phase changes and the heat associated with phase changes, there's a lot of terminology, and so it can be hard to kind of keep it all straight. So I'm just going to kind of go ahead and look over here at my iPad, and what you'll see, should be able to see my iPad on the screen. So this is kind of what we did in class. We kind of focused in on this chart where we plotted temperature versus time. And what we saw was, and you can see this kind of in the red line, that as the temperature graph went up, okay, so we kind of see that here as it went up, all right, it plateaued in spots. And it's these plateaus where it kind of gets confusing, because we see the temperature go up, pause, kind of level out for a little bit of time, okay, because remember this graph is versus time, and then keep on going up. And so what we concluded in class was that there was energy that was being used to actually perform the phase change. None of the energy was actually going into increasing the temperature or the overall kinetic energy of the particles, but, or I should say temperature is the average kinetic energy of particles, but instead the energy was going into actually changing the substance from a solid, which was down here, and I'll go ahead and just mark that. This is the solid phase down here, to the liquid phase here in the middle, and then upwards into the gas phase. Okay, so we can put a G up here to denote a gas. Okay, so we have solids, liquids, and gases. Okay, now the other thing that we wanted to zoom in on was that we have these words like fusion and solidification. We have these words like condensation and vaporization. And what these words imply is the direction of the phase change, whether it be from, let's say, solid to liquid or liquid to solid, but also not only this direction of the phase change, but also, what kind of phase change it is. So for instance, we might be adding heat in fusion and vaporization. However, one is from solid to liquid, the other one's from liquid to gas. So it's very important that we understand this terminology. So I'm going to kind of go ahead and I'm going to focus on these four terms. Okay? First of all, they all start with the molar heat of ... Okay? This implies that it is an energy needed to kind of create this phase change per 1 mole of substance. Okay? Now, there are 4 of these that we are concerned with, 2 of which we will primarily focus on, and that is going to be the molar heat of fusion and the molar heat of vaporization. Okay? The molar heat of fusion and vaporization both involve heat input. Okay, so they're both, first of all, endothermic processes. The other thing which is kind of important to focus on is because they're endothermic and they have a heat input, okay, that means that we're adding heat to our system. Okay, whatever it is. So like, for instance, if I go back here, heat here in fusion is going from solid to liquid. Okay, so I'm just going to kind of draw an arrow here. It's going from solid to liquid, and in the process, I am adding heat. Okay, I'm adding it. So if we go back to this slide here, typically speaking, this delta H fusion, delta H vaporization is going to be positive. Okay? Now, for water, pretty sure the number for fusion is right around 6 kilojoules. It's like 6.01. And the molar heat of vaporization for water going from liquid to gas is right around 40 kilojoules. Okay? Now remember, because these are molar heats, they are going to be per 1 mole of substance, which we see happening kind of right here. Okay? So what we're going to do is we're going to say, all right, this molar heat of fusion is actually 6 kilojoules per 1 mole. And this delta H vap is going to be 40 kilojoules per 1 mole. Okay? Now, if we were to use this information, if we were to go ahead and we wanted to use it in a calculation, we could take, this is obviously, and just so you know, these values here are for H2O. That's a very important clarification that I probably should have made sooner. Okay? It's important if we're going to use these in a calculation to know how to use them. So let's look at 3 examples here of how to use these in a calculation. Let's say that I have 7 grams H2O, 3 moles of H2O, and 60 grams H2O. Okay, now I'm going to specify a couple things here. First of all, I'm going to specify that this is a liquid, this is a solid, okay, and this is a gas. Okay, now I'm going to tell you that I want you to convert this 7 grams of H2O from liquid water, okay, to water vapor, or to the gas. And 3 moles H2O solid, I want it converted into liquid water, okay, or changed into the state of liquid water. And the gas, I want converted into a liquid as well. Okay, but here's the interesting part about this. We are actually starting we are going to a liquid in both this case and this case, but we have to be conscious of the fact that we're starting with a solid here and a gas here. Okay, so let's go ahead and do this. I'm going to zoom out a little bit here, and I'm going to go ahead and just move some of these other ones down out of the way. Okay, so we have some space to work. So I'm going to zoom in here on this 7 grams H2O from liquid to gas, and I'm going to set it up first and foremost with what I know, and that is the 7 grams of H2O. And the very first thing I should do, or I should recognize, is that anytime I'm given grams, especially in chemistry and thermochemistry and stoichiometry, I need to convert it to moles. So if you go to the periodic table and you look up 2 hydrogens and 1 oxygen, you'll find that when you add their molar masses, it comes out to being 18 grams per mole. So I'm going to go ahead and put 18 grams per 1 mole here. Okay, and that way we see that the grams are going to go ahead and cancel out. Okay, now I'm left with moles. But ultimately, the question I have to ask myself is, how much energy does it take to convert this 7 grams of water from liquid to gas? All right, so now I have to ask myself, well, which one of my substances, which one of my heats deals with going from a liquid to a gas? So I go back up here and I think, well, I have delta H fusion, delta H vaporization, but I'm a little unsure as to which one goes from liquid to gas. So I go back to my phase chart and I look and I say, okay, here's the liquid, and here's the gas. So I'm going from here to here, so that would be vaporization. Okay, so now that I have that in place, I'm going to go back and I'm going to say, okay, if it's delta H vaporization, then I'm going to use 40 kilojoules per 1 mole. So for water, it takes 40 kilojoules per 1 mole. I'm going to put the 1 mole in the bottom here, and I'm going to put my 40, positive 40 kilojoules up here. And what we see happen here is now the moles cancel out, and I'm left with kilojoules. And that's perfect, because I want energy. That's what I'm looking for here. I'm looking for energy, and how much energy it takes to go from liquid to gas. So now it's just a matter of taking 7, dividing it by 18, and multiplying by 40. So if you'd like to do this with me, you can go ahead and take out your handy-dandy calculating device. And we're going to go 7 divided by 18 times 40 is 15.6. Okay, and because I should probably be more conscious of significant figures, but for this problem we'll just assume 3. So this is going to be 15.6 kilojoules of energy. And because it's positive kilojoules, that implies heat energy input. Okay? Okay, now let's go ahead and focus on our next one. And I'm going to go ahead and just move it up so that we can work underneath it. And here we go. This time we're already giving it, and we're given the problem in moles. So this one's a lot simpler. We're going to just start with what we're given, 3 moles H2O. But this time we're going from solid to liquid. Okay, so if I go back to my chart here and I say, okay, solid to liquid, so I'm focused in on, okay, solid to liquid, so I'm going from here to here. Well, that's fusion. So over here, I see that the molar heat of fusion for water is 6 kilojoules per mole. So down here, I'm going to go ahead and say, okay, for every 1 mole, it requires 6 kilojoules to go from ice, solid water, to liquid water. So I'm going to go ahead and I'm just going to cancel out the moles and multiply. And this one I don't even need my handy-dandy calculating device, because I see that it works out to be 3 times 6, and I know what 3 times 6 is. It's 18 kilojoules. Okay, so 18 kilojoules is what I have as far as energy input. Again, heat energy input to melt the solid ice into liquid water. Okay. The last one is a little bit more challenging because it's a gas to a liquid. And if we go back to our chart and we look at gas to liquid, we see that, well, it's kind of the opposite of vaporization. We can focus in on it right here. It's actually condensation. And this poses a little bit of a challenge for us. So what we do, okay, is we go over here and we say, well, if it's the opposite of vaporization, mathematically that's quite simple. Anytime we have the opposite of something, okay, we just kind of use a negative instead of a positive, or a positive instead of a negative. So if delta H fusion, okay, is 6 kilojoules, then delta H solidification is a negative 6 kilojoules. And if the delta H vaporization is 40 kilojoules, because it's heat input, then the heat output is just the opposite, negative 40 kilojoules. Okay, so we can use this in our last conversion. We see that, hey, it's negative 40 kilojoules. It's just the opposite of vaporization. So I go back and I say, well, that's easy to convert. So I'll use that 60 grams H2O. Like the first problem, I'm going to have to convert this to moles. So 18 grams of water per 1 mole. Okay, then I say for every 1 mole, it requires negative 40 kilojoules. Remember, we're going from gas to a liquid, we're using the molar heat of condensation, which is just the opposite, and it is a negative 40 kilojoules. Okay, that negative implies that the heat is leaving the system. That is an exothermic process. Okay, again, just like up here, because fusion and vaporization are endothermic, which we can see here on the screen. Okay, endothermic. Condensation and solidification are exothermic, means that heat will ultimately leave or exit the system. So, go all the way to the bottom here. Now we can just use our handy dandy calculating device to take 60, divide it by 18, and multiply by 40. Negative 40, excuse me. So we take 60, divide it by 18, multiply by a negative 40, it is not cooperating this morning. And, aha, it's a negative 133. So that water vapor must lose 133 kilojoules of energy in order to go from liquid water, or from gaseous water, water vapor, to liquid water, or to condensate. Okay, this is kind of how the molar heats of fusion, solidification, vaporization, and condensation work. If you have any questions, you can please ask them. Otherwise, I hope that you have a good day. If you do have any questions, you can leave a comment on this video on YouTube, or you can email me or contact me at my website, http://bclassroom.com. Thank you for watching, and I hope you have a wonderful day.